The next question is A2physics 5, May 06, question 2. And question 2a, sketch a graph to show how the magnetic flux density B near long straight current carrying wire varies with the current I from the wire. Now you don't need this equation anymore, but I'm going to give it to you in case you have to use it. So this is for a long straight wire, the magnetic flux density equals mu naught I over 2 pi, the distance away from it. So we'll call it R, or they've called it A, I think. Yeah, distance A, so we'll leave it as A. So that means that B is proportional to I, and therefore you're going to get, when you see the graph, you're going to get a straight line going through the origin. On figure 2.2, sketch a graph to show how the magnetic flux density B near a long straight current carrying wire varies with distance A from the wire. So this time B is proportional to 1 over A, and therefore it's going to go down then, like that. Okay, it's going to be a downward curve. Describe an experiment to investigate how magnetic flux density inside a long straight solenoid depends on the current in the solenoid. Structure your answer using the headings provided. A label sketch of the apparatus worth 3 marks and experimental procedure worth 3. A suitable graph to display pattern of results 1 and conclusion 2. So there's in total there's 8, 9, 10 marks for that question. So it's really worthwhile making sure you can do that properly. So label sketch of the apparatus. Well, obviously you're going to have a solenoid. And you're going to have some way of measuring a current in it and some way of varying the current. So either a variable resistor or a variable power supply I've got here. You're going to have some way of measuring your magnetic flux inside the coil. So you have to make sure that your Hall probe or whatever you're using is right down in the middle of the coil, because remember the magnetic flux, if you think about the pattern around there, it gets much less intense at the end, and they suggest that it's roughly about half. And so if you put in your Hall probe there, remember that the slice has to be perpendicular to the field lines. So this is, and then some kind of detector, and they use a millivoltmeter. And then you use a calibration curve to change your millivolts that you record here into magnetic flux densities. So you've got the Hall probe, you've got your millivoltmeter measures. It measures this B field and converts them into, by converting into voltages. You've got your solenoid, ammeter, and variable power supply. Experimental procedure. Right, the first thing is that you should say that your detector, which is your Hall probe, is correctly aligned. So Hall probe slice must be, the semiconductor slice must be at right angles to field lines. And then you're going to vary the current and measure the current using the ammeter. And then you're going to record values of voltage from Hall probe and convert into values of B using a calibration graph. So vary I, repeat with different values. Suitable graph to display a pattern of results. So you're hoping that you're going to get a graph of B versus I. And you should know that B is equal to mu naught, the number of turns times the current in the solenoid. And so B is proportional to I, and that should give you a straight line through the origin. So B is proportional to I is your conclusion, and it should be a straight line through the origin to get you your 2 marks there. and that should be written, of course, in continuous prose.